Hi, I'm Peter Haines, a geologist with the Energy Geoscience team at the Geological Survey. In today's webinar, I'll be describing what I believe to be the world's oldest salt deposits, preserved on a basin-wide scale. These occur near the base of some of Western Australia's Neoproterozoic basins, and I'll discuss the implications that has for helium prospectivity. I'll start with a brief introduction to helium and its geological context, as not everyone will be familiar with that. In recent years, helium has been added to the Australian Government's list of critical minerals, the only gaseous element on that list. Critical minerals are defined as metals, non-metals and minerals that are considered vital for the economic well-being of the world's major and emerging economies, yet whose supply may be at risk due to geological scarcity, geopolitical issues, trade policy or other factors. While individual governments publish their own lists, helium is found on many of them, including those of the US and EU governments. Even though helium is the second most abundant element in the universe, it is rare on Earth. It's also the second lightest element, hence its popular use as a lifting gas in balloons and blimps, and being a noble gas, it's completely inert and forms no compounds. A very important property is it has the lowest melting and boiling point of any element, such that liquid helium only exists in the 3-degree window just above absolute zero. There is no substitute for helium when temperatures that low to absolute zero are required. Helium has numerous high-tech uses, particularly in cryogenics, such as cooling MRI machines, supercomputing, etc. Hence the demand and price of helium just keeps going up, and this is projected to continue well into the future. On Earth, there are two sources of helium. Firstly, helium is present in the mantle and core, so-called primordial helium, that was present in the gas and dust from earlier supernovae that accreted to form the Earth. Helium from the upper mantle can leak into and through the crust, and helium-rich mantle-sourced vents are currently being explored as a future source of helium in places like the African Rift Valley. Secondly, helium is produced, particularly in the crust, during the radioactive decay of uranium to thorium, the alpha particle thus emitted being a helium nucleus. Helium isotope ratios can distinguish the source, as the rare isotope helium-3 is present in primordial helium but not produced during radioactive decay of uranium. In sedimentary basins, as is the focus of this talk, the helium is mainly, though not always, from the radioactive decay of uranium either in the underlying basement or to a lesser extent within the basin itself. Helium that has access to pore fluids can migrate upwards through the crust, particularly through porous sedimentary rocks. The high mobility and small atom size means that most free helium in the crust is lost into space over geological time. Migrating helium can also be trapped in subsurface reservoirs analogous to the trapping of hydrocarbons, and can actually be trapped along with hydrocarbons. To date, almost all commercial helium has been sourced from hydrocarbon wells, typically gas wells, as a minor byproduct of hydrocarbon production, although there is now increasing exploration for standalone helium sources. Helium can be separated from the waste gas stream, and quite small concentrations, much less than 1%, can be economic, depending on the size of the field, infrastructure, proximity to markets, etc. High helium concentrations, say greater than 1%, are relatively rare. The United States was the first producer, starting back in the 1920s, and has always been the biggest producer, with non-US production only becoming significant since the 1990s. The big spike in production in the 60s and 70s, seen on the figure, resulted from the Cold War and space race when the US was stockpiling helium. This national helium reserve was stored underground in a depleted gas field at Amarillo, Texas. The stockpiling has now been discontinued and the reserve is being depleted. Australia has only been producing helium since 2010, where the only production is from gas piped to a refinery in Darwin from the Bayu-Undan field in the far offshore Murraba Basin. This gas is only about 0.1% helium at the wellhead. Australia currently produces about 4 million cubic metres of the world's total production of 160 million cubic metres of helium per annum. Let's now look at how to form a helium accumulation, and we'll be just considering crustal radiogenic helium here. First, we need a radiogenic helium source, that is, uranium-bearing rocks in the basement or within a basin. An Australian proterozoic basement is typically quite radiogenic, so the source isn't really an issue locally. But note that helium production is a slow process, so time is an asset, and also much of it remains trapped within minerals, and lesser amounts will be available to migrate. We need a migration pathway. Free helium needs access to the gas phase in pore fluids, which should be widely available once the helium is within a sedimentary basin. Next, we need a porous reservoir, trap and seal, the same as conventional hydrocarbon fields. But if we want to trap and accumulate helium in the long term, a very good seal is required because of the extreme mobility of helium. And at this point, I should add that salt, such as halite and anhydrite, form the best known seals. We generally need a coexistent hydrocarbon source, as helium is rarely commercial by itself. But this may change in the future. Various helium concentration mechanisms are known, but most are hard to predict and explore for. In the US experience, most helium-bearing fields were discovered accidentally, and specific concentration mechanisms only elucidated later. Once the mechanism is understood, it can be targeted for exploration. However, I think there is a very simple accumulation method that doesn't require fancy concentration mechanisms and is fairly easy to predict and explore for. This simply involves exploring in old basins with old traps that have existed a long time beneath a perfect seal, specifically salt. Although we typically want a coexisting gaseous hydrocarbon source, this should be marginal so as not to excessively dilute the helium. In the US experience, where most helium production has occurred, the highest concentrations tend to be in the older basins, and Paleozoic is an old hydrocarbon basin in US terms. And helium deposits are often on the edge of gas systems, therefore there is a marginal gas charge, and salt seal is not uncommon. Also, accumulations tend to be found most commonly near the bottoms of basins, close to the basement source. This is a mechanism applicable in Australia, where we have a wealth of old stable basins and some of the oldest preserved salt in the world near the bottom of those basins. Let's now look at the Intracratonic Centralian Superbasin, which in Western Australia includes the Officer, Western Amadeus and Murraba Basins, and other components in the Kimberley region and beneath the Canning Basin. Although now separated due to latest Neoproterozoic and Paleozoic tectonism, these basins share a similar stratigraphy, and their depositional systems are inferred to have been linked in the Neoproterozoic. They were also presumably linked to the Adelaide Rift Complex in South Australia that evolved into a passive continental margin during the mid-Neoproterozoic. A very generalised Neoproterozoic stratigraphy of the Centralian Superbasin is shown at right. In this talk, I will just be focusing on supersequence 1, that lowermost yellow interval deposited during the Tonian period of the early Neoproterozoic, which contains a basal sandy siliciclastic unit overlain by a more extensive mixed evaporite carbonate shale package. There was widespread deposition of evaporites during upper supersequence 1. Preserved salt, including halite and anhydrite at depth, shown in purple, is known from drilling and seismic in the Amadeus Basin and over a significant part of the Officer Basin. Locally, the salt has been mobilised into diaperic structures that were active at various times during and after deposition. These penetrate through the overlying stratigraphy and may reach the surface. Halite does not survive at surface in the modern environment, but sulfate evaporites, hydrated to gypsum at the surface, may be found locally. In other cases, evidence of evaporites at the surface is limited to pseudomorphs after evaporite minerals. In the Northern Adelaide Rift Complex, there is particularly abundant evidence of diaparism during sedimentation, but as yet no reports of actual preserved salt, although it may still be there somewhere at depth, at least locally. Similar age salt is also known in the small Polder Basin in South Australia, though it's unclear if this was linked to the other salt systems. While the depositional age of the salt is not precisely determined, it is inferred to be within the window of 800 to 830 MA. This diagram shows the stratigraphy of supersequence 1 in the Amadeus and Officer Basins. In the Amadeus Basin, the salt is confined to the Gillen Formation of the lower Bitter Springs group. Basal black shales of the Gillen Formation appear to be a hydrocarbon source, and a subsalt reservoir may be provided by basal sandstones of the basin, such as the Heavy Tree Formation, where present. What is inferred to be an equivalent salt unit lies in the lower Brown Formation of the Western Officer Basin, and the laterally equivalent Allinia Formation on the South Australian side of the border. A second salt unit is present locally in the Upper Brown Formation. Possible hydrocarbon source rocks are inferred in the subsalt section, but there is very limited data on this at present. And basal sandstones of the basin, including the Townsend quartzite and equivalent Pinion sandstone near the South Australian border, could provide a local subsalt reservoir. While older preserved salt is known, for example Paleoproterozoic salt drilled in Russia, such occurrences tend to be localised, and I believe these Australian salt units form the oldest known basin-scale salt units. I'll point out that the regional correlations are not restricted to lithostratigraphic similarities, but are also strongly supported by biostratigraphic work by my colleague Heidi Allen at GSWA and earlier work by Dr. Kath Gray, formerly of GSWA. That these salt units can trap hydrocarbons and helium is adequately demonstrated by exploration wells in the NT part of the Amadeus Basin. In fact, only 3 wells have drilled beneath the salt in the Amadeus Basin, but the most recent, GSWA, is currently suspended just below the salt and above a hoped-for reservoir, so there's very little information available on that hole at the present time. Hopefully drilling will be completed in the future. The other 2 wells, McGee 1 and Mount Kitty 1, reached basement, and both wells reported gas flows to surface with hydrocarbons and exceptional helium values of 6.2 and 9%, respectively. Isotopes indicate the helium is of radiogenic crustal source, and other radiogenic gases such as argon are also present. Apart from helium, these wells also demonstrate the existence of a subsalt hydrocarbon source, presumably the lower shales of the Gillen Formation, which had TOC values up to 0.8% in McGee 1. And they prove the integrity of the salt seal to trap helium over a very long accumulation time, because the traps probably formed either at the end of the Neoproterozoic or even earlier. An issue with both wells that limits the commercial potential of the discoveries was the lack of a good reservoir. A thin, relatively tight sandstone was present at the base of the succession in McGee 1, but a basal sandstone was completely absent in Mount Kitty 1, where production was actually from the fractured and weathered granitic basement. You'll notice the gas in both wells has a high nitrogen content, a common feature of high helium wells, and Mount Kitty also had 11% hydrogen. This is very interesting to note, as geologists are now starting to investigate natural sources of hydrogen as well. Where else in the basin might we look for subsalt helium? Well, it looks like the southeast margin has issues with a lack of good reservoir. The northern part of the basin in the NT contains a thick Paleozoic succession, meaning that the salt near the base of the succession is mostly too deep to drill through. In between is a potential Goldilocks zone with mostly Neoproterozoic strata. This is where GSWA was sited on a very large, seismically defined subsalt closure. This zone extends west into Western Australia. Although there is no useful seismic or deep drilling in WA, we know the Gillen Formation is present in outcrop, and it is considered very likely that salt is preserved in the subsurface, with abundant structural evidence of salt tectonics. Furthermore, the basal sandstone of supersequence 1 is well exposed around the northern and southern edges of the basin and is typically thicker than in the NT. There is also outcrop evidence of thicker basal Gillen formation shale, the potential hydrocarbon source, although source rock properties cannot be determined from the weathered surface outcrop. Salt is imaged on seismic close to the WA border on the NT side. Although there is no useful seismic in the WA part of the basin, and there is extensive sand cover, structures such as fold hinges and closures and faults can be mapped using aeromagnetic data by utilising a first vertical derivative filter to enhance subtle near-surface stratigraphic variations in diagenetic or detrital magnetic minerals. Numerous anticlines and synclines can be mapped out with an overall salt tectonic deformation style. Possible diapiric structures are noted in the geophysics and also in outcrop. Some of the apparent faults may actually be salt wells, marking the position of former salt walls that have been removed by salt withdrawal or dissolution. Structures are difficult to map in the far west near the western tectonic margin of the Amadeus Basin because it is overlain by thin Canning Basin cover, here shown in light blue-grey on the right. This is a purely schematic, not to scale, north-to-south cross-section of the WA Amadeus Basin, simply to illustrate hypothetical hydrocarbon and helium traps. Those beneath the salt, which are shown in pink, are best suited to trapping both hydrocarbons and basement-sourced helium, assuming there is actually a subsalt hydrocarbon source. Several possible Neoproterozoic source rocks are also identified in the post-salt stratigraphy and could hypothetically supply hydrocarbon charged to post-salt traps, although these are less likely to trap significant helium. Here are some field photos from the WA Amadeus Basin. At top left and centre we see weathered outcrops of the lower Gillen Formation shales, and at top right contorted and folded bitter springs group typical of salt movement. In some locations in WA, the exposed Gillen Formation contains stromatolites that also occur at the same level in the NT, providing a biostratigraphic link. At bottom we see outcrops of basal sandstone units, the Dean Quartzite in the south and Heavy Tree Formation in the north. Even though these sandstones are often strongly silicified around the tectonically affected basin margins, some outcrops away from faults, like the flat-lying Heavy Tree Formation in the lower right, are quite porous in outcrop and may also be so at depth beneath the basin. Now on to the Officer Basin. There has never been any dedicated helium exploration in the basin, but similarities to the Amadeus Basin indicate good prospectivity. I just want to point out on the map the exposed Walner diapir that I'll be discussing shortly, as well as several deep drill holes. The drill holes in WA include GSWA, Lancer 1 and Empress 1A that manage to fully core the salt where it is relatively thin near the western margin of the basin, and reach the underlying sedimentary and igneous basement. Being stratigraphic holes, these were not drilled on recognised traps, and so no hydrocarbons or helium were expected, nor were detected. Exploration well Camper 1A intersected a thicker salt succession in a more basinal position, but was not drilled on a well-defined trap at the subsalt level. All of these holes lacked a significant subsalt reservoir, but such a reservoir is expected to be present further east and southeast. In SA, near the WA border, two exploration wells drilled to basement, Mullywara 1 and Kajara 1, both intersected salt, subsalt shale and a subsalt basal sandstone unit. Numerous minor gas shows were recorded over this part of the stratigraphy, indicating the presence of a hydrocarbon system around this level, although effective trapping does not seem to have been achieved at these locations. Further evidence of a hydrocarbon source in this part of the stratigraphy comes from shallow mineral exploration holes in WA that are indicated on the map, which contain bitumen and oil shows at around this level. The presence or former presence of salt in the Officer Basin was first indicated by outcropping remnants of diapirs, including the Warno diapir shown here, but there are a number of other examples. This diapir pierces through the thin Permian cover of overlying extensions of the Canning Basin, indicating upper Phanerozoic movement, and some diapirs are inferred to have moved as recently as Cenozoic times. The subsurface of the core of the Warno diapir was investigated by a relatively shallow stratigraphic drill hole in the early 1970s by the Bureau of Mineral Resources. This hole intersected halite below 200 metres, with anhydrite, gypsum and carbonate encountered nearer the surface, where halite has been dissolved. A number of subsequent hydrocarbon exploration wells encountered halite outside of diapirs, with Camper 1A, which I pointed out earlier, being the only one to drill right through to basement underneath. The best data on the salt comes from two fully cored GSWA stratigraphic holes, with the picture here showing cored salt in Lancer 1 at about 1460 metres. Some interval halite in these trays have been partially dissolved during drilling. The halite is a dark orange-red colour and is interbedded with dolomite at this locality near the basin margin, but thicker and more massive halite beds are expected towards the basin depot centre. You won't be able to read the details here, but this is just to illustrate the aerial extent of seismic data in the WA Officer Basin, which is limited, and also to show a couple of examples of structure mapping from GSWA Report 98, which was published in 2005. These are just a couple of summary figures, and the large plates in the report are much more detailed. The first structural map of near base of the Officer Basin succession is effectively a base of salt map. While the base of the salt deepens eastwards into depot centres, there is also the indication of potential subsalt closures, and in the east we would also expect a subsalt reservoir unit to be present because it outcrops around the edge of the basin in that direction. Subsalt closures were likely to have formed quite early, at least by the late Neoproterozoic, which was the time of the last significant tectonism. The top of Brown Formation map at right is effectively a top of salt map, which shows an abundance of elongate highs, interpreted as salt anticlines, diapirs and salt walls. Also note the big gap in seismic data along the trend of the depot centres further east towards the South Australian border. While there is very limited drilling of any sort and no useful seismic in this large swathe of the WA Officer Basin extending towards the border, we can make inferences that the salt extends across much of this area and also on the existence of a hydrocarbon system based on data from just over the border. I'm here showing some snips of a log from Mulyawara 1 in South Australia, taken from the Well Completion Report. Note that there are two salt horizons, shown in white. The lower, at least, is inferred to be continuous with the lower Brown Formation salt. As I mentioned before, there were abundant minor gas shows, extending for over 1,000 metres of the lower part of the hole, indicating some hydrocarbon generation has taken place in this part of the stratigraphy, and there is a sandstone with reservoir potential at the base, but apparently no effective trapping at this locality. Perhaps the salt was too disseminated to form an effective seal, or the structure wasn't closed at this locality. Finally, some conclusions. I believe that the world's oldest regional, that is basin-scale, salt seal is present in the Amadeus and Officer Basins and is possibly preserved elsewhere in the Centralian Superbasin. The salt concealed early traps at the bottom of the basin, some probably formed as early as the Neoproterozoic, allowing a very long accumulation time for radiogenic gases such as helium. A marginal subsalt gaseous hydrocarbon system is demonstrated, at least locally. Reservoir sandstone is also at least locally present beneath the salt. The effectiveness of this hydrocarbon helium play is demonstrated by both of the wells drilled through salt to basement in the eastern Amadeus Basin, although good reservoir didn't exist at those localities. The western end of the Amadeus Basin, including that in WA, may be a better bet with reservoir and possibly also hydrocarbon source, but subsurface data is currently lacking in that area. The WA Officer Basin is yet to be explored for helium, but similarities to the Amadeus Basin make for similarly good prospectivity. I believe the ingredients look to be in place for a world-class helium province in Western and Central Australia, but the impediments to exploration include remoteness, access issues and lack of data. Finally, I'll leave you with a selected list of reports and papers that provide further information on aspects of this talk, or general aspects of the geology of these basins in WA. Most of these are GSWA publications that can be downloaded as PDFs from our online bookshop.